Hello everybody. Today is a very important lesson. I can factor using GCF, dots, trinomials, and completely. Structure is very important when it comes to factoring. To keep us structured, we have a song. And basically what we need to do whenever we're factoring is we need to first look for a GCF, then look for dots, then look for trinomials and determine if we're going to be using bridge, which will be in a later lesson. Grouping will be in a later lesson. And then we want to ask ourselves if we can factor any further. So let's hear our song. There's a second verse to the song, which we're going to get to later on in a later lesson. But for now, we're just going to hear the first one.
Whether you're building dynamic network models or forecasting real-world behavior, Neo4j is
Factor GCF, Trinomial for Let's hear that one more time. Factor GCF, Trinomial for All right, so first thing to look for whenever we're factoring is a GCF. What's a GCF? Well, GCF is short for greatest common factor. A greatest common factor is the largest number or variable that goes into every term. So, is there a GCF? Yes. The GCF in this example would be 4 because 4 goes into both 4x and 8. So, once I recognize that there's a GCF, I put one set of parentheses. The GCF goes in front of the parentheses, and to determine what goes inside, I divide by the GCF. 4x divided by 4 is x, 8 divided by 4 is 2. And that's it. I always want to ask myself if I can factor further. In this case, no, I can't factor further. We'll talk more about that when we learn the other types of factor. Now, what we're doing when we're factoring is we're creating an equivalent expression to the original, and I'm making the original expression into something times something. So if I were to go backwards and do 4 times x plus 2 by distributing, I will always end up with what I started with. I don't have to do any of this right now within this problem, but I'm just trying to show you what I'm doing. I'm taking an expression and I'm creating an equivalent expression that makes it something times something. Let's skip ahead to number 3. Is there a GCF? Well, there's no number that goes into every term. However, there is a variable in every term. So my GCF would be x. So it's the same procedure. I divide both terms by the GCF. The GCF goes outside, one set of parentheses, and to determine what goes inside, I'm dividing. X squared divided by x is x. 7x divided by x is 7. That's my answer. If I want to distribute it out, then I would end up with what I started with. I'd like you to pause, try number 4 on your own, and then unpause. Okay, now that you tried number 4 on your own, is there a GCF? Yes. 2 goes into both of them. Also, there's an x in both of them, so my GCF would be 2x. So my GCF goes in front of one set of parentheses. 2x squared divided by 2x is x, minus 4 divided by 2 is 2. The x's cancel, y. And that's your answer. All right, skipping ahead to number 7. Is there a GCF? No. After a GCF, the next thing I look for is dots. Dots stands for difference of 2 squares. So let's break down that phrase. Difference. Difference in math means subtraction. 2 means there's 2 terms, and squares are perfect squares. So let's talk about what perfect squares are. Perfect squares are the product when you multiply a number by itself. So 1 times 1 is 1. So 1's a perfect square. 2 times 2 is 4. 3 times 3 is 9. 4 times 4. 5 times 5. 6 times 6. 7 times 7. 8 times 8. 9 times 9. 10 times 10. Now, with exponents, you know whenever I multiply something, I add the exponents. X to the first times x to the first is x to the second. X to the second times x to the second is x to the fourth. So these are my perfect squares. X to the second, x to the fourth. X to the third times x to the third is x to the sixth. X to the fourth times x to the fourth is x to the eighth. X to the fifth times x to the fifth is x to the 10th. So let's take a look at our perfect squares when it comes to exponents. What do you notice about all of the powers? Well, they're all multiples of 2. And it will always be the case that perfect squares, as far as exponents go, are multiples of 2. So for variables, perfect squares have powers that are multiples of 2. Now, to take the square roots, let me just make this fit. To take the square roots, let's take a look at my perfect squares and my square roots. The square root of x to the second is x to the first. The square root of x to the fourth is x to the second. The square root of x to the sixth is x to the third. X to the eighth is x to the fourth. X to the 10th is x to the fifth. What am I doing in every case to get the square root? Well, I'm dividing the power by 2. If I divide each of these powers by 2, I end up with the corresponding square root. So to take the square root, I divide the power by 2. So, if I ask you, is x to the 20th a perfect square? The answer would be yes, because it's a multiple of 2. To take the square root, I'm dividing the power by 2. The square root of x to the 20th would be x to the 10th. X to the 100th is a perfect square because 100 is a multiple of 2. To take the square root, I divide the power by 2, so I would end up with x to the 50th. If I said, is x to the 25th a perfect square, the answer would be no, because 25 is not a power of 2. Even though 25 is a perfect square, the integer 25 is a perfect square, x to the 25th is not. So, we just did a lot of talking about perfect squares. Again, dots stands for difference of 2 squares. It must be subtraction, it must be 2 terms, and both of those 2 terms must be perfect squares. So when I look at number 7, we already said there is no GCF. So is there difference of 2 squares? Well, is there subtraction? Yes. Is x squared a perfect square? Yes, because the power is a multiple of 2. Is 64 a perfect square? Yes, because it's on my list. So yes, it's dots. Once I recognize that it's difference of 2 squares, it's always 2 sets of parentheses. It's always plus and minus. We always take the square root of the first term and put it first, and the square root of the last term or the second term and put it second. So what does that mean? Once I recognize it's dots, I make 2 sets of parentheses, 1 plus 1 minus, square root of each. The square root of x squared is x. The square root of 64 is 8. That's my answer. Once I recognize that it's dots, it's always 2 sets of parentheses, always plus and minus, always the square root of each. Square root of x squared is x. Square root of 64 is 8. Number 8, is there a GCF? No. Is it difference of 2 squares? Well, is it difference? Is there subtraction? Yes. Is y squared a perfect square? Yes. Is 36 a perfect square? Yes. It's dots. I want you to pause, try number 8 on your own, use number 7 as a model, and then unpause. Now that you tried it on your own, once I recognize that it's dots, 2 sets of parentheses, plus and minus, square root of each. Square root of y squared is y. Square root of 36 is 6. Number 10. This one's a little tricky. I want you to try it on your own. It's a very common mistake that you might make. It's okay if you make that mistake. You're going to learn from that mistake. And if you don't make that mistake, great. Pause. Try number 10 on your own, and then unpause. Okay, now that you tried number 10 on your own, let's see if you made this common mistake. There is no GCF. It is difference of 2 squares. So once I recognize that, 2 sets of parentheses, plus and minus. I take the square root of the first term and put it first. So since the 9 is written first, the square root of 9, 3, goes first. The square root of k squared, which is k, goes last. Yes, it matters. Addition is commutative, so it doesn't matter the order for addition, but subtraction, it definitely does. So the order definitely does matter. Okay, let's skip ahead and let's try number 13. This one might look a little more scary. The first thing you need to look for whenever I'm factoring is a GCF. Is there a GCF? No. Next, I look for difference of 2 squares. Is there subtraction? Yes. Is 9x squared a perfect square? Well, let's break that down. 9. Is 9 a perfect square? Yes. Is x squared a perfect square? Yes. So 9x squared is a perfect square. Is 16 a perfect square? Yes. Is y to the 4th a perfect square? Yes. So 16y to the 4th is a perfect square. So yes, it's dots. Once I recognize that it's dots, it's always 2 sets of parentheses, always plus and minus, always square root of each. Square root of 9x squared. Well, let's break that down into smaller pieces. The square root of 9 is 3. The square root of x squared is x. So the square root of 9x squared is 3x. The square root of 16 is 4. The square root of y to the 4th is y to the 2nd, because we divide the power by 2. So the square root of 16y to the 4th is 4y to the 2nd. And that goes last. I want you to try number 14 on your own right now. Use number 13 as a model. So please pause. Try number 14 on your own, and then unpause. Okay, now that you tried number 14 on your own, first thing to look for is a GCF. There is no GCF. Next, we look for dots. Difference, there is subtraction. 100y to the 4th is a perfect square. 49t to the 6th is a perfect square. It's dots. Once I recognize it's dots, 2 sets of parentheses, 1 plus, 1 minus, square root of each. Square root of 100y to the 4th is 10y squared. Square root of 49t to the 6th is 7t to the 3rd. And that's it. All right, next. We're going to take a look at 15, 16, 17, and 18 all at the same time, because there's a couple of steps to this procedure, so I kind of want you to see 4 examples at once. So let's just kind of get this set up here. 15, 16, 17. All right, we're good to go. So again, the first thing to look for whenever you're factoring is a GCF. Is there a GCF? No. A GCF must go into every term. 4 and 12 have a common factor. 4 goes into them, but 4 doesn't go into x squared. X goes into both of these, but it doesn't go into the 12. So no, there is no GCF. Can't be dots because it's 3 terms. Dots is always 2 terms. 3 terms is a trinomial. All of these are 3 terms. They're going to all be a trinomial. So once you recognize it's a trinomial, Trinomial is always two sets of parentheses. Always put the variable in front for each. Now the signs. First sign comes down. So since this is a plus, this is a plus. First sign comes down. First sign comes down. First sign comes down. Now for the second sign, the signs need to multiply to the second sign. Here's what that means. A positive times a negative is a negative. A positive times a positive is a positive. A negative times a positive is a negative. A negative times a negative is a positive. Now, I'm looking for two numbers that multiply to the last number, and then either add or subtract to the middle number depending on the sign. If it's a minus, it subtracts to the middle number. If it's a plus, it adds to the middle number. So we're going to list all of our factors of 12, starting with 1. 1 and 12 multiply to 12. 2, 2 and 6. 3, my 2 came out weird. 3 and 4. Those are all the numbers that multiply to 12. Which of those pairs subtracts to 4? 6 and 2. Bigger number goes first. Number 16, what multiplies to 2? 1 and 2, that's it. I need them to add to 3. Do 1 and 2 add to 3? Yes. Bigger number goes first. 15, they have to multiply to. Start with 1. 1 and 15. 2 doesn't go in. 3. 3 and 5. 4 doesn't go in. Those are all my factors of 15. I'm looking for the pair that adds to 8. Well, 3 and 5, 2. Bigger number comes first. And for 18, start with 1. 1 and 20. 2 and 10. 3 doesn't go in. 4 and 5 goes in. That's it. Which pair subtracts to 8? 10 and 2. Bigger number goes first. That came out a little weird. Now, let's say you're bad with your times tables. There's a trick I'm going to show you right now. And to use this trick, we do y equals the number that we're multiplying to divided by x. And then we go to second table. So if I don't know my times tables and I don't know what multiplies to 20, I can go to my calculator. I can go to y equals. I can do, in this case, I want to multiply to 20, so I do 20 divided by x. I go to my table, and now I have all the values that multiply to 20. So that's something that will help you if you are not great with your times tables. Let's skip ahead to number 20. I want you to try it on your own. Just one little hint I want to give you. In this example, we're looking for two numbers that multiply to 12 and subtract to 1. So try 20 on your own. Pause. Try it again. Pause. Try number 20 on your own, and then unpause. Okay, now that you tried 20 on your own, it's a trinomial. There's no GCF, there's no dots, two sets of parentheses, x in front for each. First sign comes down, positive and a negative is a negative. What multiplies to 12 and subtracts to 1, 3 and 4, bigger number goes first. Little twist on number 25. There's no GCF. It's not dots. It is a trinomial. But because it's x to the 4th and x squared, when I make my two sets of parentheses, instead of putting x and x, I put x squared and x squared. It's going to always be that middle term. And technically, it's a trinomial as long as the first power is double the second power and the third term is a constant. From here, it's the same thing. First sign comes down. Positive and a negative is a negative. What multiplies to 12 and subtracts to 4, 2 and 6. Bigger number goes first. Let's skip ahead to number 27. First thing I need to look for whenever I'm factoring is a GCF. Is there a GCF? Yes, my GCF is 2. So now I kind of switch back into GCF mode. I divide both terms by my GCF, one set of parentheses, and the GCF goes in front. To determine what goes inside, I divide. 2x squared divided by 2 is x squared. 50 divided by 2 is 25. Now, at the end of our song, we said, can you factor further with? Can this be factored further? Yes. There's no GCF, but this is difference of two squares. There's subtraction. X squared is a perfect square. 25 is a perfect square. So now we switch into dots mode. Two sets of parentheses, plus and minus. Square root of each. Square root of x squared is x. Square root of 25 is 5. A very common mistake is for students to leave off the GCF. That GCF comes down. Technically, can you factor any further? Is there a GCF? No. Dots? No. Trinomials? No. GCF? No. Dots? No. Trinomials? No. That's why structure is so important. It's so important that you always look for a GCF, then dots, then trinomials, then ask yourself if you can factor further. I want you to try number 28. I want you to pause, try 28 in your own, and then unpause. Okay, now that you tried 28 in your own, is there a GCF? Yes. One set of parentheses, GCF goes in front. Can I factor further? GCF, no. Dots, no. Trinomials, yes. So I factor the trinomial, x and x. First sign comes down. Negative and a negative is a positive. Multiplies to 5. Subtracts to 4. 5 and 1. Bigger number comes first. GCF comes in front. So whenever you're factoring, first look for a GCF. Then look for dots. Then look for a trinomial. We'll talk about bridging grouping in a later lesson. And after you factor something, always ask yourself, can you factor any further? See ya.